Okay, let's start today's class. Today we will review how use the impulse response HT or HN to determine the causality and stability of LIT system, and then to review the convolution properties. Actually, those two things are very important for us to why. Do you remember what we talked about in chapter 2? Yeah, some properties, I'm right, and how to get a convolution sum and how to get a convolution integral, I'm right. We talk about many examples. Actually, the most important thing for chapter 2 is how to calculate output using convolution sum and convolution integral. But here, I want why I review the chirality and stability for a system of a LIT system, and why I want to review the convolution properties, because those two things are very important for the next classes. Yeah, because from the next chapter we will talk about Fourier series. Yeah, these two things can help us to understand that. We will use those two things. Yeah, this goes. And okay, what is causality of we talk about some properties for system, am right? Any system will have some properties. Yeah, what properties we talk about in chapter 1? Do you remember? Yeah, memoryless. Yeah, stable or stable, unstable, like a chirality, chiral or not chiral, and like a like a linear or non-linear, time invariant, invariance or not time invariance. I'm right. And we also have talk about one like a inverse system. If this system is inverse system, but that is not the for the point important one in chapter 1 and chapter 2. And for the chirality of LIT system, actually, for any system, we can talk about if it is memoryless or not memoryless, if it is linear or non-linear. And here we want to talk about for a LIT system, how to define, how to decide it is chiral or not chiral. And let's try to review how to decide it is chiral or not chiral. Yeah. The chiral is just like a decide, which means the output just like depends on the present input signal and the past input signal. Am I right? Yeah, but for the LIT system, we talk about it. Talk about this in last class. Am I right? Yeah, how? How specifically how we decide the LIT system. Let me ask you a question. If we want to decide this LIT system is chiral or not chiral, does it depend on input signal? Does it depends on input signal? Yeah, for the regular signal, for any signal, it depends on the input signal. But for a LIT system, does it? Yeah, that's the reason why we talk about causality of LIT system and stability of LIT system. Actually, if you want to tell a LIT system is chiral or not chiral, it doesn't depend on the input signal. It just depends on what? Try to remember what we talked about in last class. Yeah, impulse response. It just depends on impulse response. Yeah, you can see we talk about this for the whole system. If just try to remember, if we talk about xt or xn, it is input signal, am I right? If we talk about yt, this is yt or yn, this which means we talk about the output, am I right? But if we talk about yt equal xt convolution with hn, yn equal xn convolution with hn, what's this? What's this? You know? Yeah, this is the input, this is the output, am I right? If you just talk about xt or xn, this is just an input signal. If we talk about yt or yn, it is output signal. But if I just use this equation, what's this? Actually, this is system. Yeah, this is just system. Yeah, the system is just the relationship between the input and output. Yeah. Okay. So, which means this is a LIT system. Yeah, for all the LIT system, we can use this equation. We talk about it in last class. Yeah, actually, it is just from negative infinity to the positive infinity, but we can divide it into two different parts. Am I right? And for this one, because you can see, if we want to tell a system is correct or not correct, we just focus on the relationship between the input signal and output signal, am I right? Yeah, for this one, you can see the input signal, the tau is just the input signal's like a tab, am I right? So if the tau is smaller than t, which means it just related to the past or the present time, am I right? Smaller or equal, yeah. This is correct, we call it correct part. But this one, the tau greater than t, am I right? So which means this is just the future part. We call it a non-correct part. And let me review. If a LIT system is correct, what does that mean? If a LIT system is correct, what does that mean? What's the condition? No. Stable and correct is two different things. If this LIT system is correct, what's the condition? Which means this is the correct part. It doesn't matter, am I right? If this part exists, it will be correct, am I right? But this part, if this part exists, it will not correct, am I right? So which means this part, we want to remove this part. If the LIT system don't have this part, it will be correct. That makes sense to you? So which means, yeah, we talk about that. This is just a non-correct part because if tau greater than t, which means t smaller than tau, which means it will stand for this part, the purple part. And the correct part is just this part, am I right? So which means this is the present time. And for this part, it is just future. And this is past. Yeah, this is the present. But it all point to the present output. That makes sense to you? And then if we want to, this is just an example, if my impulse response is like this, and my output should be like this, and this is just my present input signal. This is past input signal. This is future input signal. Oh, let me ask you a question: is this system correct or not correct? If I have those three parts, if I have all those three parts, yeah, it is not correct because it has this part. Yeah, that makes sense to you? Okay. Then which means if we want to this system correct, we need the impulse response only has this part. That makes sense to you? That's the reason why I said if we want to decide the LIT system is correct or not correct, we just see the impulse response. Am I right? We just check the impulse response. If it only have this part, it will be correct. If it has this part, it will not be correct. Am I right? Yeah, this is correct. And then let's talk about the stability of LIT system. For the stability of LIT system, we know if we want to check LIT system is stable or not stable, and we just check the impulse response. we don't need to check the input signal. Am I right? Yeah, we talk about this. This one can decide our IP system is stable or not stable. Yeah, which means for the DT stable, this is just a change of DT RIT system. If for your DT RIT system, if your impulse response sum together smaller than infinity, it will be stable. And this is just the CT stable condition. Am I right? We talk about last class. And RIT system with a finite unit in response, finite length is always stable. And also for the DT RIT system, if we have a DTR system, the impulse response with this format, we can be represented as this format. And then what's the condition for if this RIT system is stable? Do you remember? You remember? Actually, if absolute A is smaller than 1 and absolute B greater than 1, and then your DTRIT system will be stable. Do you know why? We talk about this in last class. Do you know why? Yeah, do you know why? Yeah, actually you can see we have Hn equal An Un plus Bn U minus N plus 1. Am I right? And what is Un? What's the name for UN? Step function, am I right? What does it look like? It just look like this. Am I right? When n greater or equal than 0 and a 1, otherwise it will be 0. Am I right? So which means for this part, the n must greater or equal than 0. Am I right? Otherwise it will be 0. We don't need to put it here. Am I right? So which means it will equal, this one will become like a An and n greater or equal than 0 plus if this one like if this what's the U negative n plus 1, which means we just let this one greater or equal than 0, right? So which means n smaller than equal 1, right? So which means n smaller than equal than 1. Then we just keep being, otherwise it will be 0. We don't need to put it here, right? So let's check this part. If A absolute is smaller than 1, for example, it is 0.5, then greater equal than 0, which means it will be just like this. This is half, this 4. Like this, right? Yeah, here. And then it just, you can use geometric series to calculate it. It is if you add if you like, it's just like if you add this one n 0 to infinity and yeah, geometric series, you can use that equation. You can see it will give you an equation like a 1 over a divided a blah 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 like that. Am I right? So you can calculate it. It is which means this part is infinite, am I right? Fixed value. And similar for this one. If B greater than 1, and this is smaller than equal than 1, which means your value to the 1 goes to this negative infinity, and here is your is greater than 1, which means this your value will be like this. That makes sense to you? So this is also a fixed value. It's not an infinity. Then you can see like add them together. Yeah, because you need to judge the sum. It is infinite or non-infinite, am I right? So which means for this, if your like impulse response have this form, and for this condition, your LIT system is stable. That makes sense to you? Yeah. Then for the CT, it's similar, but it just because for the CT system, usually your impulse response will have this form. And then similar thing, the A should smaller than 0 and B should greater than 0. Then you can guarantee this equation, guaranteeing this one, guaranteeing this one and this one. That makes sense to you? Yeah, then your system is stable. Yeah, okay. Any questions so far? Yeah, this is how can you tell your system is stable or not stable, correct or not correct? Let me ask you one question. Yeah, I just asked you, if we want to decide a RIT system is stable, do we need to check the input signal? Do we? No. What things we should check? Yeah, impulse response. Similar for the stability. If we want to tell this system is stable or not stable, what should we check? Yeah, impulse response. Yeah, and for the correl, it's just like we just check if impulse response only have this part. Am I right? And for the correlative, for the stable, we just check this equation works or this equation works. That makes sense to you? Yeah, we don't need to care the input signals. Okay, and then I just talk about why we want to because last class we talk about the stability, like the correlative and the stability, and we talk at the beginning of this class we talk about why we want to focus on the stability and the correlative of LIT system because those two and all the convolution properties will help us to compute and understand the content we will learn in chapter 3 for your series. That's the reason why. Yeah, because you can see correlative and the stability seems now useful here, but it will be used for the chapter 3. Okay, let's try to review the examples. Actually, this example we talk about. Yeah, this is your impulse response. Am I right? Yeah, and then let's talk about it is stable or not stable, it is correl or not correl. Yeah, you can see if we want to talk about LIT system is stable or not stable, we don't need to care the input signal, am I right? We just check the input response, am I right? And for this like input response, firstly, there is an equation. Yeah, this one converges if we have this limitation, am I right? Yeah, if we want this equation converges, like this is a condition for that, which means if we want the Hn converge, because if we want to check this okay, if we want to check the Hn stable, if we want to check that this LIT system is stable or not stable, we need to check Hn smaller than infinity or greater than infinity, or if it is smaller than infinity, that makes sense to you? So which means we need to check if we need to check if it is converged, am I right? So which means we just try to check this limitation thing to check if it is smaller or greater than 1, am I right? That makes sense to you? Okay, and then we have this one. Yeah, this is An plus 1. Here is Hn plus 1, right? Here is just Hn. You just put Hn plus 1 here, and this is Hn here, right? And do you know why the Un plus 2 disappear? Do you know why? What is Un plus 2? What is Un plus 2? Yeah, which means this part, if it is greater equal than 0, it will be 1. other way, which means it is -2, am I right? It is just like that. This, am I right? Yeah. And this is U and plus 2. And which means if you divide this one and this one, actually this one is very close, am I right? So which means the UN here, try to write it down, and it will be easier for you. Limitation and this one is just n plus 1, 3, power 3, n plus 1, and u plus 2. Since here is plus 1, so here is plus 3, right? That makes sense to you? Yeah, and then here it's just n3 u n plus 2. Am I right? That makes sense to you? Yeah, since this one is just goes to infinity, this is a limitation part. If n smaller than -2, am I right? This one will be 0. It is meaningless, am I right? So which means the n must be greater equal than -2, am I right? Am I right? So if n equal greater equal than -2, which means if n greater equal than -2, but which means this one also is 1. That makes sense to you? Yeah. So we can, this is 1, this is 1, we can remove it. Right? If it is n smaller than -2 and greater smaller than -2 and greater than -3, this one will be 0, right? This is for convenience, so this is meaningless. So which means for this situation, we can remove it. So then we can have this one because it has a limitation part, and also we can remove this. And then if you just expand these equations, you can get this one. Yeah, this is just 1/4, and this is just like try to move it. And then based on the limitation thing, this one is 1/4, because this will go to infinity. This one, because n goes to infinity, this is a very large equation. This is also very large, but this is very close, so it can be removed. Am I right? So this is 1/4, which means this one, which means the n equals 0 to infinity, which n converge. Am I right? This is the conclusion we can get, and then we can like we know this is stable or not stable. Yeah, it's stable, but it's smaller than if it converges. Am I right? So let's talk about the corral, not corral. It is corral, not corral. I think this one is easy. Yeah, that's right. Because you can see UN plus 2, which means it is n greater equal than -2. It will have this part. Am I right? Okay, that's great. Okay, yes, this is not corral but stable. Okay. How about these two LIT system? Let's check the first one. It is corral or not corral? Yeah, it is corral. Why? Yeah, just for this part, just in the like a positive part. Am I right? And then it is like stable or not stable. Yeah, let's try to. Yeah, they are not just anything. They are just impulse response. Well, we know that. And if we want to check it is stable or not stable, we need to use this equation. Am I right? Also, we can use this equation. Yeah, if we use this equation, which means yeah, for this equation, like n negative something like n. Yeah, since here n should greater equal than 1, am I right? So it should from 1, like am I right? It will from here, am I right? So what's the value for this one? You know? Yeah, we just get this one. Actually, it will go to infinite. Yeah, because we can see if it is 1, then the value is 1, right? And then half, right? And then like 3 and 4 and 5. Yeah, it's not like the geometric series, am I right? Yeah. And but for this one, yeah, we call it a harmonic progression. And for this one, choral or not choral? Yeah, choral. The same reason. This is choral and unstable. This is choral. And also it is stable because we use this equation. Yeah, you can see if you want to use this equation, the P should greater than 1. You cannot let it equal 1. If it is equal 1, it's not geometric series, it's not P series or geometric series. That makes sense to you? So this one is choral and stable. Any questions so far? Any question? Okay. And then let's try to, there are some homeworks. Determine the chorality and stability of the following LIT system based on their impulse responses. Okay, how about this one? What choral, not choral? Yeah, not choral because it involves a negative part. Stable or not stable? Yeah, actually, for now, you need to use this one here, which means if absolute A is smaller than 1, it will be stable. Am I right? So what is A here? Yeah, it is stable. So, okay, I will talk about it later. How about this one? Yeah. Oh, choral, not choral. Are you sure? Yeah, which means negative n plus 4 will greater equal than 0, right? Which means n will smaller than equal than 4. So it's not choral because it involves the negative part. And then, oh yeah, stable, not stable. Yeah, here you need to use this part, am I right? Just now you use this part here, and the B should greater than 1, absolute B, and but for this one is smaller than 1, so it is not stable. Yeah, also you can use some the equation, geometric equation, like to calculate it. How about this one? Choral or not choral? Yeah, that's right, not choral. Stable or not stable? Yeah, actually, if you don't know, sometimes you just need to, yeah, we know that what's UN plus 4? N is N UN plus 4, which means if N plus 4 greater or equal than 0, it will be 1, am I right? Which means N greater or equal than negative 4, am I right? Okay, which means 1, 1, 2, 3, 4. It's similar like this. This is UN plus 2, so plus 4, am I right? What is UN? UN is the when n greater or equal than 0, it will be 1. It should like this. All right. This is UN. If those two like minus with each other, what's left? Yeah, only the left set. Yeah, this one. All right. So this is our HN. All right. Choral, not choral, not choral. All right. Like if you add this value together, it's the infinite or non-infinite, infinite or yeah, finite. Yeah, it is finite, right? So it is stable. That makes sense to you? Yeah. So how about this one? Yeah, I think yeah, this one. Just use this equation. You can see for this is UN part. This is the smaller than 1, am I right? This is the like a negative n part. This one should greater than absolute greater than 1. It will be stable, am I right? So this one should be stable. Okay. Yeah, that makes sense to you? Okay, how about this one? Yeah, this is just use this equation here. If a is smaller than 0, for the t, there is ut. If a is smaller than 0 and b is greater than 0, it will be stable. So how about this one? It is smaller than 0, am I right? Yeah, if it is a -2, it's just a shift. It will not affect the stability. So it is stable, am I right? So how about the correlate? Are you sure? Yes, it is. I think it is. Yeah, mu t -2, which means t -2 greater equal than 0, t greater equal than 2, am I right? So it should be similar like this. Yeah, so it is correlate. Yeah, I'm right. Yeah. So how about this one? Yeah, similar, but you can see this is negative t, am I right? Negative t, you can check here. The b should greater than 0, am I right? So if this b greater than 0, no, so it's not stable, am I right? Yeah. Correl, not correl. Yeah, not correl, because it will go to the opposite direction. Yeah, not correl, not stable. How about this one? Yeah, if you see this one, actually you can use you can see if you want to use this one, what's the a here? What's the a here? What's the b here? If you there is it should have the like exponential part, but there is no exponential. So what does that mean? What's the a value? What's the b value? Are you sure? Should be 0. Yeah, it should be 0, which means a is 0 and b is 0. Am I right? Yeah. And actually, sometimes if you cannot use this equation, am I right? So you just need to write it like draw it. Yeah. What is ut? Ut this one, am I right? What is ut -2? T greater equal than 2, am I right? It is just 1, 2. This one, am I right? If you minus it, it's just left this part. That makes sense to you? So correl, not correl. Yeah, stable, not stable. Yeah, yeah, because it's just one part. Yeah, how about this one? Actually, this one is, if you draw it, it's just similar like this one, am I right? Yeah, because the t is absolute, you can, yeah. So for this one, what's correl, not correl? Yeah, because it has the negative part. Stable, not stable. Yeah, actually it is. It can be run like this, am I right? So for this part, what is it's just like yeah, there is no t, no ut, but you can see this for this one it is you can use this one, am I right? Yeah, because you can see t greater equal than 0, it will be called this one. T if smaller than 0, it have this part because the negative negative t, am I right? So stable, not stable. Just use this one. A smaller than 0, am I right? And like b greater than 0, am I right? That makes sense to you? Yeah, one is -1, the other is 1. Yeah, so stable. That makes sense to you? So this one is like a non-correl but stable. Am I right? Yeah. So why? Let me just give you why we talk about the stable or not stable. Like for a LIT system, like stability and correlative, we just use it for the chapter 3. Yeah, ready for the chapter 3. And then what else we will use for chapter 3? The convolution properties. Yeah. For the convolution properties, what you can think of? Yeah, distributive. The first one is a very important one, shifting property. Am I right? Yeah, this is the convolution shifting property. Yeah, and the second one, commutative properties. Yeah, just change the order. And the distributive property is just like remove the parentheses, and then yeah, And the next one is associative properties, which means you can change the. Sorry, I think this one is I haven't changed, and this is just like a associative like a property. Am I right? Yeah, those properties are very important for us to understand, to compute in chapter 3. Okay, then we finish the chapter 2. Yeah, we have already finished the chapter 2. And I will review the midterm 2 on Friday, and we will have an exam on next Monday. That means, is that okay for the chapter 2? Yeah, you can have a cheat sheet, and then we will talk about. We have some times, and I want to talk about any questions so far for the chapter 2. Yeah, we will summarize for the chapter 2 next week and next class. And for now, I want to talk about midterm 1. Yeah, actually, for the midterm 1, I check your cheat sheet. Yeah, you don't have cheat sheet. I don't think you have a very good cheat sheet. Yeah, actually, I talk when I give you the class. When I give you the class, I just sometimes I tell you, oh, you need to put this to your cheat sheet. You better to you can see this one. You should put this like this thing to your cheat sheet, and it will help you to resolve these problems. That makes sense to you? Yeah, because you can see the first one. It's just like we talk about the first one actually when we review the midterm 1. Like it's just similar like this. The first one is just like it's just like this. It will quickly convert to 0. And when we talk about it is class 1, am I right? And right side is exponential signal, and if a equal here we will here is negative. Sorry, we will net energy. And for the negative 2, you can see this one is just like it's just like this is UT, right? This is UT minus 2, am I right? And you add them together, it's just like this, am I right? And if it will convert to 2, am I right? The value will convert to 2 is absolutely the class 2, am I right? Yeah. So for the the third one, and actually it's similar with the first one, but this is just the discrete time signal. It's just similar like this one. It's similar like this very quickly drops to the 0, equal to 0. It's a class 1, am I right? And the 3, 4, and 5 is just a periodic signal. That makes sense to you? Yeah. So when when you do the when you prepare the cheat sheet, just prepare like put useful information into your cheat sheet. Yeah. Yeah, and then for this one, yeah, you don't need to, yeah, because there are so many signals, am I right? You don't need to like put the specific example, but you just remember when we talk about the signal transformation, there is a rule, am I right? What's that rule? Shift first, and then scaling and like inverse, am I right? So which means you can see for the first one, you shift it to the left 2 units, am I right? It will go to the -4, am I right? And then you just do a scaling. Here is 2 greater than 0. It will shrink, am I? It will shrink to half. It's just like this. Am I right? Yeah. So the similar. For the question 2, you need to pay attention. Especially we have already finished the chapter 2. Yeah, for the question 2, you need to pay attention. Here, it is multiple, am I right? So, but in chapter 2, we learn the convolution, am I right? It's 2 different things. If there is a convolution, if this is a convolution, you can use shifting property. But here, it's multiple. It's different, am I right? So the first thing is you just try to find xt minus 1, am I right? What is xt minus 1? It's just a right shift to left to 1 unit, am I right? Right shift to 1 unit is just like this. This is your xt, am I right? And what is your delta t? Delta t is just this one. And what is your delta t minus 1? Actually, it should be like this, am I right? But there is a minus, it's negative, so you flip it. And then what you multiple, you multiple the value, this value and this value with the original signal, which means you just get this value and this value. That makes sense because this is 1, am I right? If this is negative 1, which means you just flip it. If this value, if here is 2, which means you need to make it larger to 2 times. If this is 3, you need to 3, am I right? Which means it is a multiple relationship. That makes sense to you? Yeah. So the last one, you need to put the equation for what is Eve xt, what is odd xt. We have an equation. This is the equation for Eve xt. If you have this equation, I think this one will be easier. One is just the original signal. The other is what? Flip. Am I right? Flip based on the y-axis. Am I right? And add them together, half. That makes sense to you? Yeah. So, any questions so far? Okay. And then for this one, I think this one is easy. Actually, at least two is homework. If you finish the homework, at least, and I think the most difficult one is just the first one. Am I right? But the first one, you need to understand this one, the derivative xt, actually, it's just this equation. The basic thing is just this equation. Am I right? Yeah, this is just the derivative t. And you can see, based on this one, you will find it's not memoryless, am I right? Yeah, because it involves a future thing. It involves yeah, I think it is just like I need to put it in minus delta t. It should the present and the past. It will not involve for future, so it will be causal. Am I right? And it will not be stable because you can see there is an example. If your signal is the same t square, and you can get this equation. Am I right? Which means your output as the t increase to the infinity, your output will be goes to the infinity. Am I right? Yeah. So which means this is now stable, and we also talk about if it is a time invariant and it is linear because derivative actually it's a linear operation. Am I right? And also there is no for the linear for the time invariant you didn't change the time. Am I right? Yeah. So this one I think is most maybe most difficult, but other things you can see here. Because it involves the future and the past, it is obvious it's not memoryless, am I right? And it involves future, it is not like horror, am I right? It's stable because you can see the x, the input is bounded, am I right? We know the input is bounded, so and the output is just equal input, no matter what the n you have, am I right? So it is stable. That makes sense to you? Yeah. And it is now time invariance. Do you know why? Now time invariant. Do you know why? Yeah. Yeah, that's right. If you found the system change, like up do something for the time, which means this is not time invariant. Time invariant means it's a natural thing. Yeah. If you deal with something to the time, this is not time invariant. But this is the linearity because this is just like the relation between the output input. It's just like there is no other things. Am I right? And for this one, you can see it is memoryless because it's just a present time. Am I right? it is memories, it is correlated, am I right? And it is stable or not stable. I think this is obvious because n will go to the infinite, am I right? That makes sense to you? It is not like it is not stable. It is time invariant? No, we have that equation. Do you know? Like we have that. Actually, you need to put. Do you remember we have like a quick tell if it is stable, if it is a time invariant or linear. There is no coefficient. There is no scaling. Do you remember that one? You should put that in your cheat sheet. All right. And then you can quickly judge if it is timely. Yeah, you can see there is it's no like there it's not it's not constant. Am I right? It involves time. So this is not time invariant. Also, there is a square. Am I right? There is a power. So it is not linear. So yeah, and similar with this one. Yeah, it is involves past time. Yeah, so no not memoryless, but it only depends on the present time and past time. Am I right? So this one is the stability because you can see the xt is bounded. Am I right? So it's just the linear relationship between the linear combination for the input and the output must be bounded. That makes sense to you? And for the time environment, it is yes, because you didn't change any time, but it's not linear. Why? Because you change the signal. We talk about that. If you deal with to the original signal, then it is not linear. We talk about that in the class. Yeah, that makes sense to you? Okay. Okay, this one I think I think you just did the question one is good. You just finished that very good. But the question two, actually this one, do you know? You need to put there is a table. I give you the table, like what's the fundamental of fundamental period, what fundamental frequency, oscillation between the relation between oscillation and the oscillation and the frequency. Do you remember that table? You need to put that table on your cheat sheet. Then you can finish this very easy because when the pi when the omega when this one if it is close to all the times pi, it will the highest when it is close to the even time pi, it will smallest. Yeah. So you need to put the information to the cheat sheet very smartly. Yeah. And this one, I think actually I give you some very similar questions. You know, you need to try to use x1 to represent x2. And because it's a LIT system, the output should have the similar thing. Am I right? So then you can easily to get y2. Am I right? Since if you have this relationship, that makes sense to you. Yeah, you can see this one is just like a shift here, and then divide this part, and then you can get the x2t. Yeah, I think I just that makes sense to you. Okay. And the next one is just follow the steps. You need to put the 4 steps to judge linear and now time invariant in your cheat sheet. Yeah, and then you can easily to finish this one. And the next one, I think, have a similar method. So when you prepare the cheat sheet, just remember to prepare smartly. If you have any questions, you just ask me. Yeah, maybe you don't know which one you need to, which information you need to put. I will give you some hint. Yeah, that makes sense to you. Actually, yeah, okay. For the midterm one, any questions? Okay. We will review midterm 2 next class. Oh, yeah, that lab. Did you check the lab? I added to the Bible. Yeah. If you have any question about that lab, yeah, just let me know. Yeah, I give you the code, but you need to finish it. Yeah, finish the code. The code is now full. Is now finished. Yeah, just yeah.